Welcome back, everyone. We're into revising electrochemistry. So far, we've dealt with redox reactions, which are a key component of electrochemistry. We recognize we can identify redox reactions, but now let's see that application to the different types of cells. We're going to do a little comparison between galvanic cells and electrolytic cells, and hopefully keep some things in mind. So, as we go to a galvanic cell, we have to recognize one of the key components of any electrochemical cell is energy transfer. So with a galvanic cell, you need to recognize that you start with chemical potential energy and you are producing electrical potential energy. So the chemical elements react to give us electricity. So a galvanic cell is just a battery. It is a chemical reaction that produces some sort of voltage for us that we can use in an external circuit. Initially, the current isn't very big, but we can put cells, multiple cells in series to get a bigger and bigger current. That's not our problem. What does this galvanic cell look like? Well, you can see it here. It's quite clear that there is no battery. There is a voltmeter that is measuring the difference in potential between the zinc electrode and the copper electrode. The part that is outside of the cell, outside of the configuration where the reactions is happening is known as the external circuit, where the parts of the cell where there are chemical reactions happening is the internal circuit. And notice in this case, we've got a metal electrode. In this case, it happens to be the copper with a solution over here that's separated by a salt bridge. That's all part of the internal circuit. Another solution and another electrode, which in this case was the zinc electrode. So you can see quite clearly there are two components to this galvanic cell. In this case, it's the zinc copper cell. Now, please don't get into your mind that we can only have questions on a zinc copper cell. That's not true. You can use any number of electrodes, a metal electrode, into a solution of its ions, another metal electrode into a solution of its ions, and that electrode could even be a gas electrode where there's gas passed over a platinum inert electrode, but there's a reaction that takes place between the gas and the solution. So it's very important to identify that. In this case, there's no battery, there's no power source, but we are giving external electricity out to the external circuit. If we look at the electrolytic cell, now what happens in an electrolytic cell is that we need electrical potential energy. We need a source of energy, and that energy creates a chemical reaction. So it's exactly the converse. It's the opposite transfer of electrons. Now, if we look at different electrolytic cells, you'll see they all look a little bit different. They also look different to the galvanic cell. Let's go and have a look at some diagrams of these cells. Here's one which was used to do some electrolysis. We started with copper 2 chloride, so we had copper ions in the solution, and we had chloride ions in the solution. And what happens is the chloride ions got converted into chlorine gas, and the copper ions got deposited over there as copper. Now, you'll see there's one container, and here's the key difference. There's a battery. This is the source of electricity. It's the thing that's making the chemical reactions take place. If you notice, at this electrode, this is a positive electrode, this is a negative electrode, and we've got some chemical reactions happening. There's no salt bridge. There's no two components. There's one component, one solution, electrodes. The electrodes over here, in this case of electrolysis, can be anything, but they are usually graphite electrodes. Okay, if we look at another example, we will recognize that in these different types of cells, the cells have names. They have the name of an anode and a cathode and a salt bridge for a galvanic cell. So if we look at the galvanic cell, we have to recognize that there are certain types of reactions happening here. In this case, zinc is going to form zinc 2 plus 2 electrons, because zinc is a more reactive metal than copper. On the copper side, copper 2 plus ions in solution gain 2 electrons to form copper. So in this case, we have reduction here, and we have oxidation over there. Now, what's important is that the zinc jumps into the solution and electrons are deposited onto the metal. That means that this electrode now becomes the source of electrons. And if it's a source of electrons, it is given the sign of negative. So it's connected to the negative terminal of the voltmeter. This is the positive terminal of the voltmeter. The electrons move in the external circuit from the negative towards the positive. This is the positive. And what we now need to recognize is that the name for this electrode here, where oxidation takes place, is called the anode. Please learn the definition that the anode is the place where oxidation takes place. And the way to learn it and remember it is just simply anox. Anode, oxidation. And over here, where we've got reduction, this is known as the cathode. And what do we look for? We look for a red reduction cat. And so it's very important that you are able to identify the anode and the cathode and recognize as well what connects these parts of the galvanic cell together, the two different half cells, is the salt bridge. Now the salt bridge is filled with ions. It's a very soluble solution, something like potassium nitrate, and it completes the circuit. The positive ions in the salt bridge, those are known as cations. They move towards the cathode. So the positive ions, the potassium ions here, will move towards the cathode. The negative ions will move towards the anode. So NO3 minus, they will move towards the anode. And in this way, we make a connection. Positive ions moving one direction, the negative ions moving the other direction. There's a free flow of charge moving, and so it completes the internal circuit. But it also maintains electrical neutrality. What do I mean by that? Because we had more zinc ions being deposited into the solution, these negative ions neutralize that. Over here, copper ions are going to form copper metal, so the potassium ions replace the copper ions, and so overall, the two half cells remain neutral. Let's move on. And if we look at electrolysis in the electrolytic cell, we recognize here that these cells don't all look the same. But there's an important thing that's happening here. Chloride ions are losing electrons. So chloride ions are losing electrons to form chlorine gas, and we've got 2 electrons being lost. That is oxidation. And oxidation is taking place here. So this is the anode. Whereas over here we've got copper 2 plus 2 electrons to form copper metal. And what you'll recognize that is a reduction reaction. So that is the cathode. And recognize something in this reaction is that unlike the galvanic cell, this one is positive. because it's the thing that is attracting the ions to the electrode, and this one is negative. So it's important to recognize that difference. Also recognize that galvanic electrolytic cells look different. You can get the ones for plating, but you can get, and they look quite different for the ones for electrolysis. But in exactly the same way, we're still saying that the anode is where oxidation takes place, and it's the positive cell. Whereas the spoon here is where reduction takes place, and it is the cathode. And I just wanted to show you that even for electrorefining, there's a solution with two electrodes, the same solution. The cathode is where you're going to get reduction, and the anode is where you're going to get oxidation. So nothing much has changed, even when you get to the chlor-alkali cell. Over here, one solution, even though there's a membrane cell between them, we still get the same sort of things happening. So be very clear about that. I want you to recognize that they all have electrolytes, and the galvanic cell, those can be molten or they can be in solution. There are two cells here. There are two half cells. And there's one cell usually here. Okay? If we go back to another comparison, they are usually different electrodes. They're different metals. These are usually either graphite or the same type of element. Although in electroplating we don't get that. So they do sometimes appear different. What I want you to recognize is very important, is in both cells we get oxidation at the anode and we get reduction at the cathode. Now, the last thing I wanted to show you is simply changes at the electrode. And the most important to recognize that, in fact, at the anode of a galvanic cell, we get a loss of mass. And at the cathode, we get a gain of mass. Now, in the same way, you'll see here, this one is the cathode and it's gaining mass as well. Now, that is for a metal that's being deposited. Guys, I suggest that if you want to do these comparisons, it's a really good way to check your learning. So make sure that you analyze the difference between the electrolytic and the galvanic cell, and make sure that you can identify each case.